In modern high-scale systems, we often trade control for developer velocity. We use languages like Java, Go, or C# because they handle memory for us automatically. But this convenience comes with a hidden cost. Behind every smooth API response lies a silent process, the garbage collector. Most of the time, it's invisible, working in the background to reclaim unused space. But as your system scales to handle thousands of requests per second, the way memory is reclaimed can suddenly become your biggest bottleneck, turning a sub-millisecond operation into a multi-second freeze. This is the reality of managed memory and production.
To understand why this happens, we have to look at stop-the-world events. When the heap, your application's memory, fills up, the garbage collector must identify which objects are still in use and which can be deleted. In many implementations, the only way to do this safely is to pause all application threads. Imagine a busy restaurant where every few minutes, every waiter and chef must freeze in place so a cleaner can sweep the floor. No orders are taken, no food is served. This isn't just a delay, it's a total suspension of service. In high-throughput systems, even a 100-millisecond pause can cause thousands of requests to queue up, leading to a massive traffic jam.
In high-scale environments, we don't just care about average latency. We care about the tails, the P99 and P99.9. While 99% of your users might see a 10-millisecond response, that one unlucky user caught in a GC pause might wait 500 milliseconds or more. This is particularly dangerous in microservices. If service A waits on service B and service B is paused for garbage collection, the latency propagates upstream. One slow node can trigger a chain reaction of timeouts and retries across your entire cluster, effectively bringing down your system through cascading failure. You aren't just measuring performance, you're measuring stability.
Most modern collectors use the generational hypothesis, the observation that most objects die young. They split memory into young and old generations. Minor collections in the young generation are fast and frequent because they only look at a small part of the heap. But when objects survive long enough, they are promoted to the old generation. This is where the danger lies. Major collections of the old generation, often called full GC, are significantly more expensive because they must scan a much larger area. If your application leaks objects into the old generation faster than they can be cleaned, you hit the dreaded full GC pause, which can last seconds and halt all progress.
Choosing a garbage collector is always a trade-off between throughput and latency. Some collectors, like Java's parallel GC, aim for maximum throughput by using all available CPU to clean memory as fast as possible. But this comes at the cost of long stop-the-world pauses. Others, like Java's ZGC or the Go collector, prioritize low latency. They perform most of their work concurrently, while the application is still running. However, concurrency isn't free. It requires more CPU overhead and can reduce the total number of requests your server can handle per second. You have to decide, do you want to process more data overall, or do you want every single request to be fast?
The best way to fix GC issues isn't always tuning the collector, it's reducing allocation pressure. Every time you create a short-lived object, like a temporary string or a wrapper class, you're adding work for the GC. In high-performance systems, engineers use techniques like object pooling or zero allocation libraries. By reusing memory instead of constantly requesting new blocks, you keep the heap clean and the GC quiet. For example, reusing a buffer for network I/O instead of allocating a new byte array for every pocket can drastically reduce the frequency of collections. Remember, the fastest garbage collection is the one that never has to run.
To master GC, you must measure it. Standard CPU and memory metrics often hide the truth because they average out the spikes. You need specific GC telemetry, pause times, collection frequency, and promotion rates. Tools like the JDK Flight Recorder or Go's pprof allow you to see exactly when and why the collector is running. By bringing these silent events into the light, you can transform a jittery, unpredictable system into a stable, high-performance machine. Garbage collection doesn't have to be a latency killer.
if you understand the mechanics behind the pause.